Welcome back. In last part of the lecture, we discussed about the intensity of the radiation defined like this, and we derived the general expression for the intensity of the radiation, which was this one, and then we again discussed the Poynting vector and the general form of the intensity. Now, in this part, I will briefly discuss about the radiation pressure, and all then we will do some numerical exercise. Okay, what does it mean, radiation pressure? As I mentioned here, if we consider a before this is a plane perpendicular to the direction of propagation of the electromagnetic waves. So, electromagnetic waves essentially will give some pressure actually. Why? Because intensity we studied na, intensity we see here, there the intensity means the energy imposed in that point P. So, essentially here in that plane, if we consider a point P and a electromagnetic wave is propagating in this direction, then the electromagnetic waves will impose the energy in that point P, or any point if we consider in the perpendicular plane. Okay, so and also for electromagnetic wave there is a momentum, we know that there is a momentum and there is energy. So, there should be a pressure actually, that is called the radiation pressure. We know that the definition of pressure, what is the definition of pressure? That is essentially the force by area, right. So, if we consider a cylinder of the unit area, then what happened, the force imposed in that point P, that will for the unit area, that will be the pressure, force per unit area, right. So, that can be evaluated, I am not doing that. The pressure P will be 1 by 3 U, and we can understand that actually that P should be related to the U. U means the energy density. Okay. So, as we discussed before, the total energy stored in the volume is U times C, right, if we consider per second, then the force should be related to that energy density U. I am not getting the derivation, but the form will be 1 by 3 U, and this is very important relation actually. This is called the radiation pressure and U is the energy density. So, if we see the unit, then it will be also consistent with the unit as well. What was the unit of the energy density? U is the energy density. Okay, so it should be unit is energy by volume, right, means joule meter square, joule per meter square. Not square, volume, it's not area, it should be cube, right, joule per meter cube if it is volume, yes. And what is the unit of pressure? It is force divided by area. Force means joule meter divided by meter square, it is also joule per meter cube. So, these two are consistent, right, it should be. So, this is the definition of pressure, and the dimension, radiation pressure dimension should be, force is m L square T to the power minus 2 if it is force, right, force is m A, velocity L to the power minus 2 divided by area, area is L square, right. So, it should be m L cube, no, not L cube, m L to the power minus 1 T to the power minus 2. So, this is the dimension of the pressure. So, this is the form of radiation pressure 1 by 3 U, but this radiation pressure is very important because this energy density is not very negligible term. If we consider the electromagnetic waves in the space, when the spaceship, different kind of spaceship was supposed to move in the space to land Mars or moon, then we have to consider that radiation pressure. Otherwise, the path followed by the spaceship will not be matched with our prediction. Okay, so now at the last we will discuss some problems related to this radiation pressure. In last class we write down a problem, in this class we will solve that problem related to the radiation pressure. Okay, first write it down. Let me write it down. In an electromagnetic field, the amplitude of electric field at a point is 3 volt per meter. Calculate the energy density and intensity of the wave at that point. Given mu naught is equal to 4 pi 10 to the power minus 7 hat 3 meter inverse. Okay, that is given, right? The amplitude is given, but that is the for electric field, not for the magnetic field. That means E0 is given. Let me solve it. E0 is given 3 voltmeter inverse. So what will be B naught? B naught should be E naught by C. So 3 divided by 3 into 10 to the power 8. What will be the unit? Unit will be meter square. So it will be 10 to the power minus 8 Weber per meter square. So this is B naught. So now just we have to calculate the energy density. We have to calculate the energy density. You know that U is 1 by 2 epsilon naught E naught square, but E naught is not given here, so we need to write it in this form, B naught square. So it will be 1 by 2 mu is 4 pi into 10 to the power minus 7, and B naught square is 10 to the power minus 8 square. So essentially it will be 1 by 8 pi into 10 to the power 16 7 minus 9. If I'm not wrong, it's minus 16 plus 7, it's minus 9. So it is actually 3.98 into 10 to the power minus 11 joule per meter cube. So this is U, but we need the intensity, right? This is the energy density, right? Energy density is already evaluated. This is energy density. Now we have to evaluate the intensity. So intensity is UC. What was the U? U is 3.98 into 10 to the power minus 11, and C is 3 into 10 to the power 8. What will be the unit? Weber meter square. So if we multiplied it, then it will be 9, 12, around 12. So and it will be minus 3. So it is 0.012 Weber per meter square. This is the intensity I. Okay, so this is a trivial problem, not formula based problem totally. Let me do another problem. Calculate the intensity This problem I have written in the last class, but we did not solve because we did not aware of the intensity formula and these things. So that's why I left that problem in that class, but in this class we will do that. The RMS value of electric field of at a distance 10 meter from a 100 watt electric bulb. Wow, good question. And given epsilon naught is 8.85 into 10 to the power minus 12 meter inverse. Okay, so this is the given materials. We have to solve it. Okay, so first we have to evaluate the area. What is given? We have they ask the intensity and the RMS value, that's right, of electric field, but there is a electric bulb. This is the electric bulb, let's say. So 100 watt electric bulb, and the 10 meter distance is 10 meter from electric bulb. The light is emitting, and light is essentially electromagnetic wave. So they want to mean that, and the power of the electric bulb is 100 watt. That means per second 100 joule, energy of 100 joule is emitting. Okay, the energy is given. So now we have to first evaluate the area, then we have to multiply the energy. Okay, let's say at 10 meter, the area of a spherical surface of radius 10 meter. What will be the area? Because we have to calculate for the total surface, right? Total surface. So that's why we need the area, which will be 4 pi r square. So it is 4 pi into 100 meter square. So 400 pi meter square. So what will be the intensity? What will be the intensity? Intensity is, we know that energy divided by time into area. So energy by time can be replaced by power divided by area. Okay, so if it is, then intensity should be power divided by area. What is the power? It is 100 watt bulb. And what is the area? 400 pi. This is the area, and unit is meter square. Okay, so it will be 0.08 watt per meter square. Probably I have told before, this is Weber, right? Not here. Yeah, it is correct. This is not Weber, this is obviously watt. What I have told, Weber is WB. Okay, this is not Weber, this is watt, joule per second. Here it is correct. And here the B, this is the Weber, correct. Okay, this is correct. This is correct. In that place, I have just mistakenly told Weber. Okay, this is 0.08 watt per meter square. This is the intensity. Okay, so now we have to calculate intensity. We have calculated the RMS value of electric field. RMS value of the electric field. That means that we have to evaluate the electric field. RMS. These terms are given to make us confuse. RMS value things. We will write down the general formula, which is into C. Yes. Okay. No, actually not. This is E naught, but ERMS. What is the ERMS? ERMS is defined as E naught divided by √2. Okay. This formula is required. RMS value is given, right? So it is E naught by √2. So ERMS square equals to E square by 2. So it is epsilon naught ERMS square. See, this is very important formula. If you don't know it, otherwise you can't do the problem. So this is the intensity, which is 0.08. So now ERMS should be 0.08 divided by E naught times C. So it is 0.08. What is E naught? E naught is 8.85 into 10 to the power minus 12, and C is 3 into 10 to the power 8. So if we do it, it will be 5.5 volt per meter. Okay, so this is the value of our ERMS. This is very important question. Very important. This formula, based on this formula. Okay. So let me summarize my today's class. First, we discuss revise the energy density part. U. Then we discuss the intensity of radiation. Which is I is equal to C times U in vacuum, or in general I is equal to V times U, where U is the energy density. And then we discuss the radiation pressure, which is P equals to U by 3 actually. And then we did some numerical exercise, among which this is very important formula, ERMS is equal to E naught by root 2. So this is the summary of this class. Also we have done some numerical exercise as well. So in the next class I will discuss the in first class we discussed the range of the electromagnetic radiation from the cosmic to radio. So in the next class we will discuss in detail the electromagnetic waves, the range of the electromagnetic waves, which are radio waves, then microwave. Then if we make it order in terms of the wavelength, then it will be for radio wave the wavelength is maximum and the energy is minimum. Okay, leave it. In next class we will discuss, probably next class will be the last class, I think. Let's see. In next class we will discuss the spectrum of electromagnetic waves from radio wave to cosmic ray. What happens? Probably it gone. Okay, from what have we written next class, spectrum of electromagnetic wave. Okay, we will discuss about this, and we also discuss the application of these radio electromagnetic waves. Okay, so let me conclude my class here, and thank you. We will meet in the next class again.